this one is y equals x plus 2 squared times x minus 3. That's already in factored form. We love that for x-intercepts. That's awesome. It's just begging to be graphed. But one thing we need to recognize that is not as obvious to some of us is the degree. This is still a polynomial. The degree of this polynomial is what?
3.
Well done. I didn't catch you guys. This is not 2. It's not a degree 2. So this guy basically is saying I appear 2 times. X plus 2, x plus 2. It's called a repeated factor. Okay? Linear repeated factor. They're both linear factors because x is raised to the first power in both cases. You can have a quadratic factor when x is raised to the second power, right? So these are both linear factors. One is repeated and one is distinct. Okay, so in reality, if you prefer, this is really x plus 2, x plus 2, x minus 3. That's what's going on here. Okay. If you were to actually expand this, and the good news is I just confirmed with my math lab, they've changed the software after years. So now you won't have to actually FOIL these out. Okay, they used to make my students FOIL every one of them out. So if you're repeating the class and you know what I'm talking about, yes, that pain and suffering is behind us. Okay, so what this is saying is, if I were, or what I'm trying to get at, if I were FOILing this out, I would have to do these two first, perhaps. I'd get something squared, wouldn't I? X times x, okay. Then when I take that squared trinomial that I would get and distribute it to x minus 3, wouldn't I get x cubed? Okay, so eventually the highest power, the degree, would be 3. But a shortcut to get that is to add up these two powers. So when you're in factored form, to get the degree, you simply add up the degrees of each factor. 2 plus 1 is 3. So the degree of this polynomial is 3. And that's because when you expand it out, you get an x cubed term. Okay, so if this is a degree 3 polynomial, I would already know something about the end behavior, wouldn't I? My end behavior, for example, just like for the one here, who's also degree 3, would mean that at the ends, I'm going in the same direction or different directions? Different directions. So we're either looking at this situation or this situation. So one of these two is at play because of degree 3, odd. Now I would look at the sign of the leading coefficient. Now here, in this case, we know that it's a 1. It's my leading coefficient. It's positive, so it's going in increasing direction. Here, though, I don't see a leading coefficient. If there was going to be one, it would come from either a number in front of one of these x's, right? Or the number in front right here. There's no visible number in front of any of those things, so we say that it's implied to be a 1, and it's positive. Had there been a negative in front here, it would have been a negative leading coefficient ultimately. So in this case, it's a positive leading coefficient. If you have a positive leading coefficient, that means that you are increasing or decreasing from left to right. Increasing, which is that one. So if I was writing out the end behavior, again, we have to talk about each piece. One piece is going to the left forever, the other going to the right forever. So I would say as x goes to the left forever, what's happening? And as x goes to the right forever, what's happening? That's standard protocol as you begin your end behavior. As x goes to the left forever, what's happening? As x goes to the right forever, what's happening? So in this case, one's going down, okay, so negative infinity. And in this case, positive infinity. So they're going to be different when it's an odd degree, isn't it? But when it's even degree, they'll be going in the same directions, won't they? Okay. So I just wanted to review that with you. So that would be the first thing I would notice.